Hello, everyone, and welcome to today's webinar entitled How Interstellar Technologies Uses Metal Additive Manufacturing to Improve Combustion Performance, sponsored by Velo3D. I'm Jim Anderson, Content Director here at engineering.com, and I'm pleased to be host for what is going to be a fascinating hour. Now, liquid rocket engine fuel injectors, well, they're critical to ensuring optimal combustion performance. Since the beginning of liquid fuel rocket engine technology, the success or failure of many major missile and booster programs has been directly linked to engine injector performance. Interstellar Technologies has had great success with metal additive manufacturing for injectors, drastically reducing part count and simplifying the manufacturing process. Injectors for rocket engines are very complex parts, and different additive manufacturing platforms require different levels of post-process machining. Today, we'll explore Interstellar's new Phoenix subscale fuel injector with real data from cold flow and hot fire testing. We'll also learn about the advantages and limitations of different laser powder bed fusion processes, how different adjustments to the printing process can improve performance, and we'll see real-world results that Interstellar has achieved using Velo3D's Sapphire 3D metal printer. And now a little bit about our expert presenters. Jeff Thornburg is founder and CEO of Interstellar Technologies, an engineering and technology development company focused on advanced research and development for launch vehicles and propulsion systems that expand our reach into the solar system. Prior to forming Interstellar, Jeff was Senior Director of Propulsion Engineering at SpaceX in Hawthorne, California, and served as the lead engineer and manager of methane engine systems, including the Raptor engine development program. He has a master's degree in aeronautical engineering from the U.S. Air Force Institute of Technology and a Bachelor of Science in Aerospace Engineering from the University of Missouri. Dr. Zach Murphy is Vice President of Technical Partnerships at Velo3D. Zach served as the Director of Business Development, Head of Product and Applications, and Head of the Hardware Engineering Group at the company, and he led the introduction of metal additive manufacturing technology for Fortune 500 energy company. Prior to joining Velo3D, Zach led North American sales for Concept Laser. He has earned a Bachelor of Science and PhD degrees in Aerospace Engineering from the University of Texas, and he's been granted more than 35 patents. Jeff and Zach, over to you.
Yeah, thanks, Jim. Good afternoon. This is Jeff Thornburg. Little housekeeping of my own real quick. I wanted to offer a couple of thanks to folks that made this possible for us today. I first wanted to thank the team at Velo3D. I've known Zach for a couple of years now, and him and his team are just a pleasure to work with. I also like to thank the CEO, Benny Biller, as well. Just a great relationship between Interstellar and Velo. And then as I get into this, I wanted to thank my team. None of this would be possible today to talk about or share with the community without a fantastic group of people at Interstellar. Special thanks go to Brock Dennison, my head of manufacturing, Emma Anjay, who was the lead engineer for the injector test program that we're going to talk about today, Sarah Ball, our head of supply chain, and Prashant Ravindran, who's our senior propulsion engineer and analyst. So special thanks to the whole team, but especially those folks to make this possible. So as an intro, I really wanted to share a little bit about Interstellar as a company as we get ready to talk about the application of Sapphire to some of our needs as a company. Interstellar Technologies was founded in early 2019 with the vision to expand humanity's presence in the solar system. Pretty grand vision, but that is the future of where humanity is going into space and how our economies will actually grow with the assets and resources provided by the exploration of space. I spent my entire career working on the problems of getting from the ground into orbit, and I want to spend the second half of my career along with my team advancing spacecraft technologies and space platforms that really unlock the space economy and focus on low Earth orbit into cislunar space and beyond. That's what excites Interstellar. That's our long-term vision. And we're starting that with an application specific to propulsion technology that we're going to talk about today. That's one of our key product areas. A little bit of word about our founding team. Thank you, Jim, for the kind intro. As was mentioned, I have spent a good portion of my career, the last 25 years, focused on rocket propulsion and launch vehicle systems, especially with my time at SpaceX, and also working with Paul Allen prior to his death on advanced hydrogen systems specifically. And then I started my career back at the Air Force Research Labs back in the late 1990s, early 2000s. Adam Harris, our Chief Strategy Officer, I worked with him at SpaceX as well. He was instrumental in the success of SpaceX in the national security space domain. He was also a former Air Force officer, a staffer on the House Appropriations Committee, and the Inspector General of the National Reconnaissance Office. And then Elizabeth Robertson, who is our Director of Operations at Interstellar, following a 13-year career at NASA, where she was a Deputy Chief Engineer on the Space Shuttle Main Engine Program, and also was the team lead for liquid engine systems and the additive engine and propulsion programs at NASA's Marshall Space Flight Center. She was also my senior manager of propulsion during our time with Paul Allen. So I show this picture when I do a lot of presentations to try to orient people that may not be too specific or in close touch with what's happening in space with propulsion and launch vehicles and even the exploration beyond low Earth orbit. This is a shot of the Saturn V when it's staging in Earth orbit right before it gets ready to take the astronauts to the moon. And this is one of those images that, for me, really tells the story of where Interstellar is focused on the technology and the capability to move people and cargo out into the solar system. And one of the ways that we're going to help accelerate that process is through advanced technology for propulsion systems and then spacecraft systems as a part of our long-term vision. And this is a great chart to kind of show what that's going to look like for all of us one day when we have the opportunity to explore the zone between Earth and the moon specifically. So our team is very experienced. I mentioned the three founders, but we have a rich heritage with over 130 years of experience across a variety of different industry and government programs. We're definitely well experienced with all of the different propellant combinations, from kerosene to methane to hydrogen-based systems and storables. And we have one of the more unique teams and capabilities in small business in aerospace for a startup in the industry today. And I'm really excited to have this group of folks with me as we kind of push the boundaries and the envelope of human expansion into space. So let's start a little bit of liquid propulsion 101 really quick. I'm sure there's folks out there attending today that are experts in their own right in propulsion, but maybe not everybody understands all of the nuances of what a rocket engine is. And a lot of times you see rocket engines on the back end of a launch vehicle, but sometimes they kind of all look the same. They all have generally the same purpose, but to set up today's conversation of the components and development of an engine system, especially as it relates to injectors, I wanted to make a couple of comments on the purpose. Obviously it's there to provide thrust to the launch vehicle system. Engineers work with three things when they design systems: conservation of mass, momentum, and energy. And the energy comes from the propellant stored in the launch vehicle. And the rocket engine is there to convert all of that energy in the propellant tanks, all that potential chemical energy into kinetic energy. And it's that momentum exchange, it's that high velocity particle shooting out the back end that provides the thrust. And so that's really the very simple explanation of what a rocket engine does. In order for it to do that effectively, the injector in the combustion chamber, you see the terms on the chart: an orderly conversion of energy. Really, it's like any other engine system. It comes down to how well that injector and combustion chamber can mix and burn those propellants with the goal of 100% conversion of chemical energy into kinetic energy. And so the goal of the engineer as they design injector systems is always striving to eke out that last 10%, that last 1%, to get as close to 100% efficiency as possible. So I also wanted to add a few words on engine cycles. There's a lot of different engine cycles. The point here is that not all engine systems are the same. But I'm fortunate to live in a time where, when I started my career, there was only a few places that you could work on engine systems. You could go to work for NASA. You could go to work with Aerojet or Rocketdyne. But there were very few places, 20, 25 years ago, where you could go to work on the development of these systems. Now we live in an era where we've really started to commercialize space, where there's so many opportunities for engineers to work on a variety of new types of systems. So let's talk about what some of those systems look like, and then who are using those type systems in the industry right now. Because we're really experiencing a renaissance in space that kind of rivals the 1960s, the late 50s and 60s, when we had the surge in the space program through Mercury, Gemini, and Apollo. On this chart, we'll start out with a couple of simpler concepts. So a pressure-fed engine system is the simplest rocket engine. You have a gas that's pressurized like helium, and it pressurizes the tanks to higher pressure, and then it pushes the propellant to the injector, and it's combusted in the combustion chamber. That's one of the simplest systems, but it's also one of the heaviest for a rocket. The higher pressure in your fuel and oxidizer tanks, the thicker the walls have to be, the heavier the rocket is, the less payload you can get to orbit. So that was kind of that's an interesting first simplified start to a launch vehicle. But very quickly, you want to get to the point where you can make the rocket as light as possible, because that translates to payload, which translates to cost. It's all about getting the dollars per pound or dollars per kilogram to orbit as low as possible to really unlock uh, routine, affordable access to space. And so, kind of the next steps were to attach pumps to rocket engines. And there's a variety of ways to do this that have a varying degree of efficiency and effectiveness. The electric pump fed cycle is kind of a newer cycle that's actually being flown today at Rocket Lab with the Rutherford engine. And so you replace a combustion device like a pre-burner or a gas generator that would normally burn a little bit of propellant and drive a turbine with an electric motor. And for smaller engine systems, this can be quite effective and reduce development cost and time, and be a good way to jump into a system with a limited amount of complexity and lower cost. These systems are typically less effective at higher and higher thrust levels because of the battery demands, electrical demands, and the weight of the electric motors required at higher and higher thrust levels. Next. On this chart, there's a couple of interesting diagrams, and these can all be found on the internet for those that are interested in studying these things further. The gas generator cycle on the left, this is like what you would find in the Merlin engine at SpaceX, as well as the J2 engine and J2X engine from NASA from both the Apollo era and the modern J2X. And there's a variety of other engines that utilize this cycle. It utilizes a gas generator that burns a little bit of propellant, drives it through a turbine, and then it kind of exhausts it out and throws it away. Anytime you throw mass away in a rocket engine, it's detrimental to the efficiency of the system, but still quite effective as a means to drive your launch vehicle. A really interesting cycle on the right is the tap-off cycle. Blue Origin uses the tap-off cycle. They take a little bit of combustion chamber gas on their BE3 engine to drive their turbine. It's another way to drive that pump system, spins up the impellers in the pump and drive the pressure to the engine system. It's also was used on a variant of the J2 engine as well in development with NASA and Rocketdyne many years ago. And before I get into this last one of the reasons I'm showing this is just kind of give a little bit of introduction to the different types of engines, and also they all utilize similar components. The cycles are laid out differently depending on the level of complexity and performance that is acceptable or required. But for those that are interested, there's a couple of great reference books out there that go over all of this information in great detail. They're kind of the aerospace engineer, rocket engineer Bible, so to speak. There's Rocket Propulsion Elements by Sutton, which is a fantastic reference. So the stage combustion cycle is representative of the space shuttle main engine, and then the expander cycle is what you would find that in the RL-10 system, which is an upper stage engine. The expander cycle is a very simplified cycle. It takes the energy off of the nozzle in the combustion chamber and heats up the coolant, or the fuel in this case, to drive the turbine. So again, all these systems have some flavor of pump, combustion chamber, and nozzle. Some of the flavors have a gas generator or pre-burner as well, but a lot more nuance than maybe what has been understood by the layperson in terms of liquid propulsion. So I wanted to show kind of where some of these components live in a real engine rendering. And Interstellar, we really leverage advanced manufacturing and 3D printing with our innovative clean sheet approach. And what we do is really different than anybody else because we've really rethought how we do design for propulsion and spacecraft systems to take full advantage of the capabilities that exist in the additive manufacturing landscape. And as you'll see later, where we're really innovating even beyond that and pushing the additive capability even farther than present day to enable unique designs and performance improvements that haven't yet been seen in the industry. And we're excited to bring that to the forefront. But on the lower part of the chart, you can see some of the basic component features of the rocket engine. The gimbal is where it attaches to the vehicle and allows the engine to move around in order to steer the vehicle. Advanced turbopumps, main injector, the main valves, lines and ducts, the nozzle, and the combustion chamber. And so just wanted to give folks that didn't know kind of a feel for where these components live and a little bit about what their purpose is in terms of the previous conversation of some of the engine cycles. So liquid propulsion hardware is really ideal for additive. And to tell a little bit of a story, when I started my career 25 years ago, it would take years and millions of dollars to work through R&D and development because of the complexity involved in being able to assemble hardware for a rocket engine system that needed to survive the extreme thermal environments that a rocket engine does. You have cryogenic temperatures on the pump ends of this vehicle, of this system, this rocket engine system, and you have 5,000 plus degree flame temperatures in the combustion chamber that are just daring to melt the whole system down. And so you'll never find a more challenging engineering environment than the development of a new rocket engine system. It requires so many disciplines. There's at least 13 different engineering disciplines involved in just the turbo machinery alone. And then there's multiple engineering disciplines involved with every component of the system and then marrying that system itself. So because of the extreme environments, it drove really extreme manufacturing techniques that drove a ton of touch labor. It drove extreme costs, which is why launch vehicle systems historically have been so expensive. One, the hardware is so complex because the environment is so extreme, and just the amount of hours required. And then these systems were also expendable, so you were throwing them away after every use, um, which is, obviously not super cost effective. So in this chart, you see some different flavors. On the upper left is an Interstellar injector that was produced on the Sapphire machine, which we'll talk more about later in the presentation. Obviously, a lot of companies out there have been printing combustion chamber and nozzle components. Turbo machinery, though, is really my first experience with additive manufacturing. And so if we kind of focus on that for a second before we get into the injector conversation, when I first started producing impellers for rocket engine turbopumps many years ago, turbopumps were really the critical path item. They were the thing that took the longest to make, that was the most expensive and the most prone to failure in both development and even in operations once you kind of closed the end of the development cycle. You've got a turbine spinning at extreme speeds, upwards of 40,000 to 90,000 RPM, depending on what kind of propellant. And then that's the hot side of the pump that's at extreme temperatures over 1200 degrees Fahrenheit and higher. And then you have these cryogenic temperatures at minus 400 degrees Fahrenheit on the other end. So definitely an extreme environment just in the pump itself. If we take the impeller for a moment, which is the component, the shiny component you see in the center of the bottom left image, a shrouded impeller like that required some very intricate machining capability to produce the desired flow paths in pump impellers. It wouldn't be uncommon to take 18 to 24 months just to produce one. And there was only a couple of suppliers in the US that really had the talent and the equipment and the experience to produce those. Obviously, at the time I started my career, there wasn't a huge demand for new rocket engines because the space shuttle engine and the space shuttle were really the predominant vehicle in the US at the time. But still, I lived in a development world where these components cost tens and tens of thousands of dollars per unit and took 12 to 18 months or more to produce. So that part itself really became the first focus for me for additive manufacturing, um, because how do you take a component that takes so much time and energy and cost and really enable fewer people in a faster time frame? And I'm excited to talk about that a little bit more with Zach today on the subsequent charts. Obviously, we have other combustion devices on the engine that help power the turbo machinery, like a preburner. In the bottom right is a public released image of the Paul Allen preburner for the program we worked with him in the past life prior to Interstellar. That was really a super fast-paced program that went from clean sheet to test stand at full power in a matter of months, which really had been unheard of since the 1960s era, where we were flush with tens of thousands of people working with the industry and a huge percentage of GDP behind it for the Apollo program. So the takeaway here is the cost and complexity overall of rocket engine hardware, especially liquid engine hardware, makes it a perfect technology area for focus of additive manufacturing, um, and a great place for Interstellar to really push the limits of what's already being done now. So we're super excited about that. But even with all that said, especially with the rocket engine impellers on the turbopumps, there is still some limits to the geometry. I mean, ideally, you have some pretty complex high angles and extreme curvature requirements within those pump impeller geometries that as a designer, you'd really want to use to make the components smaller and lighter and higher performing. But even up till recently, we've had these limitations that most people that work in the industry and work with additive understand what the 45-degree rule means. As you change to these angles with these overhangs, as you see in this image, it gets more and more difficult to maintain structural integrity as well as surface finish. So as good as additive is, there has still historically recently been some limitations in the geometries we can acquire. And then the other part of that, especially for impellers, but also with every other component, the ability to have to use support structure to obtain some of these desired geometric features is problematic, because sometimes you require support structure to make your creation real that you could never fully remove, or the removal of that support structure is very costly and time intensive. And so this has been another focus of Interstellar working with Velo is enabling the capability of the print machines to to make our creations come to life, our design improvements come to life by eliminating that support structure completely, which really helps us focus on reducing that post-processing time. Um, and I'll tease what we're going to talk about later with the injector, but because of these improvements, we're able to create parts that can come right off the print machine and go straight into the test facility, which it was unheard of not so long ago. And I'll invite Zach to comment here a little bit as well, but um, we can go ahead to the next chart. Some of these challenges are on this chart as we seg from that last one. I've mentioned a lot of these things already, but also, when you talk about NDT and qual insert, Zach's going to talk about that a little bit more here in a second, but all those things are critical. When we first started using additive a few years ago, there was a lot of concern about, flying these parts on different launch vehicle systems and our ability to qualify and certify that. We've come so far with our ability to produce additive hardware for engine systems with the material properties required to survive those extreme environments. So when you take a system or systems like Interstellar is developing, where we have quite a bit of reusability and life required of our parts, the early days of additive, the material properties really didn't lend themselves to that. But with the improvement in the technology, especially over the last 5 years, and then now taking a step beyond that with Sapphire, really helps with our longevity and our life of our parts and our ability to run it through the test programs that our customers are going to require and do require for certification and qualification. For us in development, though, it's really all about that time for post-processing, like I mentioned before, speeding the pace of development, which is great, but also that translates into production as well. So when we look at our first product, or one of our first products, which is our Phoenix engine system, it's not just about using additive for development, but also how that development cycle translates into production, because this is an all additive system, and that's where the industry is moving. That's the right way to go, and we have more work to do on the post-processing front, especially when it comes to support structure and heat treatments, et cetera. But I think that's a nice place to kind of invite Zach to kind of jump in and talk about some of the ways that we're tackling these challenges on the print side.
I really appreciate it, Jeff. And my goal here is to provide a little bit of background as to what Velo is trying to accomplish and how we're working with companies, especially like Interstellar, who are really pushing the boundaries of what's possible and utilizing our technology to advance their systems pretty dramatically. As Jeff mentioned, one of the parts that has always been a really good candidate for metal additive manufacturing is a shrouded impeller, which you see on the right. And this is one of our kind of canonical parts for Velo 3D, because it's a part that we really focused on when we were developing our process and our system to extend the capabilities of laser powder bed fusion, which is what our system does. So you can see here on the top, this is how you would need to support a shrouded impeller if you were building it on a traditional laser powder bed system. And all of the red lines that you see are support structures. And so if you were to print this on a conventional system, you could print it, but then you have to deal with getting those support structures out in order to have a usable part. And this really makes the laser powder bed fusion a non-viable solution for these very complex geometries with internal passages. And so Velo 3D set about to develop a process and a system that could really extend the capabilities of metal AM to the point where they would start to be much more widely useful across a range of applications. So this bottom picture shows how you would print the part on the Sapphire system. And what we've been able to do here is to eliminate all of the internal support structure. So you can print this part without any internal support structure, meaning that your time to a finished part is dramatically reduced. So your iteration cycles become much faster. And the cost of the end part is also dramatically lower. And the way that we accomplish this is really kind of a twofold process. So we focused pretty intensely on process control and metrology to be able to operate our system in a much tighter process window. And this is what really enables us to print the low angles, and then to change the machine architecture in such a way that you can print low angles consistently and know that you're going to get good quality parts out at the end of the day. So as Jeff mentioned, one of the main drivers for using metal additive manufacturing is to reduce the iteration cycles and get to a final system configuration much more quickly. And it's definitely an effective tool in that regard. But in addition to speed, one of the other things that you have to deal with is cost. And I like to say that engineers will always find a way to make something. If they need a part, there's always a way to manufacture a part. But often that comes at a pretty hefty cost. And if you're looking at making a complex system like a rocket engine or turbo machinery, you can get those parts, but it's going to be relatively expensive. So not only are we able to reduce the design cycle time to get these parts, but the cost is also dramatically reduced, because a lot of the cost of additive parts is really in the post-processing. And we see examples where almost half of the final part cost is due to post-processing. So if you can reduce that as well as reducing the cycle time, then you really started to kind of democratize the manufacturing of some of these really complex parts and systems. What is our system capable of? When we look at the applications where we can really provide quite a bit of benefit, turbo machinery and rocket engines have a lot of the geometries that capitalize on our technical capabilities. So if you look at some of the examples we have on this slide, on the left-hand side, we have impellers or turbine components. And really here, what we're using is our low angle capabilities. And this impeller that you see here is actually 0 degrees on the shroud at the exit of the shroud, on the OD of the impeller. So the shroud is completely horizontal at that point. We're able to print down to 0 degrees without using a support structure, which means that this part doesn't require any support removal at the end of the day after you finish printing it. We also are able to print tubes, as this middle picture shows, with very large inner diameters. So whenever you're trying to route fuel or oxidizer or any other fuel into through manifolds and through pipes, these large inner diameter tubes become very useful. And we can print these up to, now we're at about 100 millimeters inner diameter without internal support. So you can really start to use the technology to print some very interesting geometries there. And then the picture on the right may not look like something that's from a rocket engine, and it isn't, but one of the things that it demonstrates is thin wall capabilities. So our system has a different recoater technology, which doesn't apply any force when it lays down a layer of powder. So it doesn't apply any force to the part or the powder bed. And because of this, we can print very thin-walled structures. And one of the places that this is very useful is if you have heat exchangers on a system, or if you're looking at like a smaller rocket engine, a smaller nozzle and combustion chamber, and the regeneratively cooled flow paths inside those nozzles and chambers. So you can really leverage the capabilities across kind of the entire system to realize performance improvements. And one of the things we realized pretty early on is that making these geometries is definitely a step in the right direction, right? Enabling people to make these very challenging geometries is what's needed to expand the application space. But one of the things that you also have to address is the quality of the parts. So if you can print very interesting geometries, but the part quality is not good or it's highly variable, then it's not really a useful solution in a lot of very high demand, mission critical type of application. One of the things that I like to quote whenever I'm talking about quality, and it's especially appropriate here, is the NASA Marshall Space Flight Center standards for laser powder bed fusion. And this quote is really, it kind of captures one of the main challenges in qualifying metal additive manufacturing, which is that the largest latent risk in the utilization of laser powder bed fusion parts in critical spaceflight application lies in the limitations to verify individual part integrity. So if I'm kind of summarizing what this says, it's that the machines that are available today are capable of making very high quality parts. But one of the challenges that you have as an engineer, as an end user of these parts, is knowing whether or not a specific part is very high quality. And so that's one of the things that VELO3D also set out to solve, in addition to the geometric limitations, was giving end customers the confidence they needed in these mission critical components. So the way we approached the quality assurance problem was from three different aspects. We have the machine health, so knowing that the system is nominally in spec and calibrated so that you're ready to start runs, and then you know your kind of complete fleet status of all the machines that you're printing on. And then to monitor the build as it's occurring and be able to infer part integrity from that data. And then the final step here is to tie all this together in an easily consumable fashion. So you have build reporting and you have traceability and documentation of not only the machines, but of the builds and the part quality once the build is finished. The first aspect of this is machine health. And this is something that seems very rudimentary, but it really is something that's not addressed in a lot of the systems that have been available in the past. And I think, again, to go back to the NASA Marshall Space Flight specs, they're requiring optical components, the optical system of these machines, to be calibrated every 90 days. And in the spec, when you read it, they basically give a rationale that says, we would like this to be done more frequently, but recognize that there's a lot of overhead and a lot of cost in doing this. So if we can do it every 90 days, that will at least suffice to give us confidence in the parts. But, and this is an important but, if the calibration every 90 days is found to be not within the specified limits, then all of the parts made in the previous 90 days or until the last known good calibration are non-conforming, which means they can essentially be scrapped. And so you could have somebody who's producing parts that has made $250,000 worth of parts that are now non-conforming. So we set out to make a system that is calibratable by the user. You can do it from a single button on the user interface and check the machine calibration before every build. So you have complete confidence that the system is nominally in spec before you build a print and every print that you do thereafter. And while it's important to know that the system's in spec for a given build, one of the other critical aspects is looking at how the system is behaving over time. So we've provided control limits on all of our critical parameters and tracking of all of these key parameters within our software product called Assure. And this is not only useful for kind of statistical process control as you're printing parts in production, but we also do this on a per build basis. So in every build, we're tracking the critical parameters, and we've provided control limits where we know that the process is good and making good parts, so that the user has a much higher confidence in the quality of the part they get out of the tool at the end of the day. So the goal here is really consistent part quality. And the way that we've gone about trying to address this is really captured in our Assure quality product, which gives the end user unprecedented traceability. You can do these pre-build calibrations with single clicks from the user interface so that it's easy to know that the system's in spec. It's easy to know that you're good to go to print parts. What you see here on the right is actually one of the readouts from the build report that shows the optical system health prior to a print, and this is included with every print. And then along with the runtime monitoring, where you have the actual build monitored in real time and real-time reporting, and the build report generation, we feel that we've captured a lot more detail around how the system's performing. And this, combined with the geometric capabilities of the VELOSapphire system, are really helping to open up a lot of new applications. And I think it's really awesome for Velo3D as a company to be working with companies like Interstellar Technologies, who are really leveraging this and really taking these capabilities that we've put together and starting to make some really incredible products out of it. With that, I can pass it back to Jeff to go into a little bit more detail about one of those.
Yeah, thanks, Zach. So, one of the questions I get all the time from people is, well, rocket engines are complicated. How do you know the parts are good? So that's why Zach's commentary was so key just now, as we kind of get into the meat of what we've been doing recently that's so exciting. There's been so many incredible developments in the industry to produce quality parts that have a great pathway to flight. And so at Interstellar, our team comes from a rich heritage of not just design and R&D, but manufacturing, testing, and flight operations for traditional as well as additive parts and systems that have gone on to do real world missions. And that possibility wasn't there even a few years ago. So as commercial companies grow and evolve and increase their capabilities and move in these technology areas, it's been exciting to be a part of that over the last decade or so. One of the things that we do better than anybody else, though, is we've really reimagined the design process. One of the things that we focused on in years past was really how do we get the industry to produce larger parts instead of kind of breaking out of that smaller 300 millimeter square bubble and move into larger and larger systems. That was an early focus of this team's energy. But really lately, our focus has really been working with companies like Velo3D and Zach, is enabling newer, creative, more robust designs that were not possible even by yesterday's standards for printing. And so obviously we're fully designing to utilize AM as the manufacturing approach in all of our components of our Phoenix engine system. And what we mean by that is that everybody's printing parts now, but there's still a lot of parts out there that are being produced that could be made by other means. And that's not the full utilization of the technology, especially from an innovative standpoint at a company like Interstellar. So, we're all in with additive and really pushing those boundaries with innovative approaches and software, working with other companies on topology optimization and other techniques to really make these new creations that we have come to life, that make the engine system lighter, higher performing, lower pump count, higher reliability, et cetera. So it's really an exciting time. Working with Zach, talking about these new qualifications and process control and getting this data all throughout the development cycle as it leads into production is really a key for us as we kind of grow into these other spacecraft systems. Obviously, we want to test hardware early and often. That's built into my DNA, the company and the team's DNA at this point. Obviously, 3D printing and additive is ideal for that. But at one point, at some point in the cycle, we meet the technology where it is. And by that, I mean, rather than levying requirements or requirements that were good for other manufacturing mechanisms onto additive is not always the right approach. So we really have dove into understanding exactly how these machines operate, exactly what their benefits and limitations are, and setting our requirements appropriately to move quickly through our development process. And that really allows us to truly design for the process in front of us. And again, a big focus of our efforts this year has really been minimizing that post-processing time across the board. So let's get into the injector real quick. I mentioned the function of an injector already, but basically you've got all of that energy in the propellant of your rocket. In the case of all these liquid systems, you've got to mix the fuel in the oxidizer as efficiently as possible, burn it, and throw it out the back end to produce maximum thrust, maximum capability based on the mass of the system and the payload you want to carry. So the goals of when you're designing an injector really are the most efficient injector elements possible, manifolded properly to give you this ideal mixing and combustion process that allows your device to create a 5,000 plus degree flame that's not melting the rest of your engine system. That's definitely one of the challenges of designing these things. And the more efficient your injector is, the more energy you're releasing, the more extreme your environments that you're having to design around. And keep in mind, we're not designing these anymore to be expendable one and done parts. These are all reusable. And so when we're talking about improved efficiency and stability, we're really talking about creating the environment where these propellants mix in a stable way and burn where they don't have these damaging oscillating behaviors. If you're burning kind of uncontrollably, you're going to see a lot of vibration and a lot of pressure swings, which can damage hardware. So you really want to limit that to the maximum extent possible for a rocket engine system and mix these things to almost perfect efficiency. So you can convert all of that chemical energy to energy moving out the back end kinetically, moving your rocket. Really what I want to focus on quickly here while we have time is why is AM such a good fit for injectors? A lot of people out there playing with this already know the answer to this question. But when you look at something as complicated as the F1 rocket engine injector on the right, that's one of the largest injectors that has ever been produced for the Saturn V rocket for the F1 engine system. So much blood, sweat, and tears went into that with thousands of people working that. And a lot of complexity in that design and the environments that it had to manage. A very challenging part. But going into the next chart, let's talk about the complexity real quick of a main injector and why AM is such a good fit. It used to be hundreds and thousands of parts needed to create an injector. And they were all made by hand and they were all very intricate. And so on the space shuttle main injector specifically, you have hundreds of individually produced mixing elements. So elements that take the oxygen, the hydrogen. And so you're taking hydrogen on the left side and they're taking oxygen on the right. And these individual elements are mixing them. And then there's an igniter that's basically a torch that kind of lights it out into the combustion chamber. But if you look at the image on the right that kind of shows a blow up of the space shuttle main engine, main injector, that's not a monolithic part. There is a ton of critical welds, brazing assemblies, and literally thousands of parts there, as well as fasteners. When manufacturing is that complicated, especially in development, you're definitely going to see failures, and certainly the Space Shuttle main engine program saw their share of failures. But the manufacturing technology at the time, that's where it was, and that was really the best way to be able to produce a part that complex. You can imagine what the price of that part is when you have that many piece parts that have to be critically assembled with very tight tolerancing to survive an environment like a rocket engine combustion chamber. So if we keep that in our mind and go to the next chart, this component more than all others is so ripe for additive because of what it offers in terms of cost and time. So you can take a very complicated injector with hundreds or thousands of parts, and now you can start to create it monolithically. And so there's a couple of examples from the public domain. The right photo shows a NASA additive injector from their additive engine programs, which was a monolithic piece. Still required some other pieces to be welded and assembled, but still, it's a great part reduction from the way they used to be produced. The Ariane 6 on the left is a really interesting piece. They wrote a public paper where they actually quoted their part count reduction. And the part that you see there, which is an injector element core for their Vinci engine, was 248 parts that was reduced to one monolithically printed piece. Now, it obviously still needs the manifolding, the housings, the faceplate, and some other features too. So it's still not truly a pure monolithic part yet, but an incredible advancement brought on by the ability of additive. And that's why you saw so much focus on injectors over the last few years with application of additive for rocket engines. So we partnered with Velo to use the Sapphire machine to test the limits of what we thought was possible with injector technology. So rather than aggregating hundreds of parts into a single digit number of parts, we wanted to produce a monolithic piece that was ready for testing, and do it first at subscale, then at full scale for our Phoenix engine that totally eliminated part count down to one, minimized the amount of time to go from the machine to the test stand or eventually the engine assembly. But there was still some things we needed. So we've innovated a revolutionary new design for injectors for liquid rocket engine systems, but we needed a little bit more from manufacturing. Our design is possible with a combination of both our design philosophy that's unique to Interstellar, and additive manufacturing. But the new capabilities we needed were in surface finishes, support structure removal, processing time, and the ability to make these things quickly and effectively in a way that was even an order of magnitude better than what's being done now. So we embarked on a program that you see in this following chart where we took two injectors, one produced with the Sapphire machine and one with the industry standard DMLS powder bed fusion, and we ran them head to head. So we were already in the midst of development testing for the Phoenix injector. We picked a design where we could do an apples to apples comparison between the two technologies. And then it was very synergistic with our ongoing test and development program. I won't be able to show all of the data today because unfortunately with COVID-19 and the coronavirus situation, obviously our supply chain has been disrupted. We've been disrupted like everybody else, but I do want to preview some of these things for you, and hopefully we can share more of this in a future webinar or a future discussion. But we did all the same cold flow testing, which is where you just run the propellants without combusting. We did hot fire testing, the same tests on both injectors. And then we did robust surface measurements and as well as geometric measurements through structured light scanning and CMM. So what did we find? Well, super interesting. We suspected and hoped that we would see the improvements, and actually we got more than what we had even anticipated. So we purposely picked one of our injector iterations that would allow us to see very clearly what these changes would look like. And what we saw, just to get to the chase, is we saw a 5% improvement in combustion efficiency. We saw a significant improvement in stability as well. Those two kind of go hand in hand, so I won't dive into all of the engineering tech speak today because we don't have time for that. But I can kind of give you some perspective. Well, what does that mean when we see that level of combustion efficiency change? And remember, these are two identical injectors that are the same in every respect in terms of their design intent and the models required. The only difference is how they were produced and the outcome of how they were produced by those two different machines. So if you say 5% in gain in combustion efficiency, that doesn't mean much to folks. So if you remember back to the beginning of the conversation, I said the key part of a rocket engine really is that injector's ability to adequately mix the propellants to convert as much of that energy in those propellant tanks to kinetic energy coming out the back end. So a 5% improvement is actually huge. It directly translates into better specific impulse, which is like the gas mileage of a rocket engine. So it's driving your grandfather's Oldsmobile at 12 miles per gallon versus driving, a modern sedan at 32 miles a gallon. It's that type of enhancement. And so let's go to the next chart that kind of cuts to the chase of what that looks like potentially. So again, on the images on the right show our Injector Phoenix test program. We have a great partnership. We're testing this at Purdue University at the Zucro Labs. Special shout out to Scott Meyer and the team there. But let's assume for a second, and then we'll jump into the conclusion, that we have two identical hydrogen engines. And the designs are identical in every way. And we have one injector that's made with a standard DML machine, and a second with the Sapphire. The improvements we've seen so far in our testing program show that there was a huge difference in the specific impulse, or quote unquote, the gas mileage of the engine systems themselves based on those manufacturing improvements. That directly translates into up to 20 to 40% more payload for an upper stage on different launch vehicle systems. And that directly translates into revenue. So if you can take your existing launch vehicle and you can now change nothing but a single component in how it's manufactured, that translates into money, and that speaks to the industry at large. Now, this was a initial preliminary assessment, so there's quite a broad range, and that kind of, if I try to bring it a little bit back to reality for a second, injector design is not that simple, right? Some are more experienced, so they can take this capability and eke out that last bit of performance they were looking at, or you don't have to have as complicated of an injector design to still get pretty decent performance. It's kind of what that translates to. But for what we've done at Interstellar, really, we have got a totally different approach to how we're even designing the parts. And that's really what's enabling the maximum amount of improvement that I'm quoting here, just to kind of give you some perspective on what it means to see these improvements in our one-to-one head-to-head programs. Obviously, we're going to continue to collect the data and continue to work with Velo. And then we hope to come back in the future and show you, the details of some additional details on surface finish and dimensional tolerancing. But all of that looks very much in line with our expectations. But it's an exciting development. It's exciting to see this technology as applied to our proprietary designs. Certainly it validates the capabilities that Zach went over earlier in the presentation of what the Sapphire can bring to the industry. And we talked a lot about pumps, but now the injectors, and this really applies to all of the different components we talked about for the system. So I'm going to ask Zach to jump in here too, but I think the conclusions for us today really were that what I just mentioned, the Sapphire continues to expand the possibilities for us at Interstellar on our propulsion development. That flexibility, you can see what that leads to, because as a business, it's still all about how you get more to your customers and how you can grow your business faster and maximize both the performance and the economics. And the Sapphire is really stepping up to answer the call of all these challenges that we presently have to kind of break through to this next level of design. And that's really where Interstellar is pursuing the next level of design for additive. So as I mentioned before, really excited to at least share this preview today and look forward to sharing more results as we get them as we move forward.
Jeff and Zach, thanks very much. A very in-depth presentation. We've got a few minutes before our hard stop at the top of the hour for some questions. There are multiple questions from the floor, so let me jump right in. Jeff and Zach, post-production scanning of the parts, CT, X-ray, how do you scan the parts? To what voxel size are you scanning? Have you run into any post-processing limitations?
I can definitely answer that for our parts in general. I think when we're looking at qualifying the mechanical properties of our different processes, we are using, we like to use directional radiography more than full CT scanning, because we can get much faster iteration and go through more samples more quickly. It allows us to do better measurements for large DOEs as we're developing processes. But generally, we're trying to scan down to recognize pores down to 100 microns and a little bit below that. And that's really kind of what we're trying to qualify when we're trying to hit our 99.9% dense part requirements, which is our internal spec.
Jeff and Zach, historically in additive manufacturing, surface finish, of course, that's been almost an obsession. For some applications, the smoothest possible surface finish is an advantage. For some, and heat exchangers come to mind, laminar flow is not your friend necessarily, and so some surface texture may be desirable. How do you manage that? Can you exploit the sort of the surface finish that you get with the process to your advantage?
I mean, this is Jeff.
So, go ahead, Jeff.
No, I was just going to say that real quick. I mean, I think that's where you have to come to meet the technology where it is, and it's a little more complicated than that. It's surface finish is directly correlated to what material you're using as well. So you have to have a really good understanding of what material do you want to work with, what kind of surface finish can you expect, and then designing for that expected surface finish instead of applying a surface finish requirement that wouldn't really be possible. But I certainly think those are are more advantages than limitations that will continue to improve as we go. But the answer to your question, yes, you could definitely exploit that to your advantage in terms of the heat transfer design requirements for your heat exchanger specifically.
Jeff, you chose Sapphire. One of the features that Zach enumerated here is that when it comes to the 3717 Marshall requirements, with calibration, with traceability, with the ability to get the paperwork in line, how much is that a cost factor or development time factor when you're building hardware?
I mean, it is a factor. I guess the best way for me to answer that question is I think a lot of people view cert and qualification, especially with some of these government standards, like it's an impossible mountain to climb or it's too cumbersome. And I think what we're trying to do, working with Zach and others in the industry, is build that data acquisition into the development process. So instead of scrambling at the end to show that you've done it right, acquire that data through the process so that it's already there when you're ready to go sell to your customers. And I think that's where the Sapphire brings a lot of capability to manage that data and bring it forward with us as we go versus waiting to the end and making it kind of a mission impossible type of scenario.
Jeff and Zach, I see that brings us to the top of our hard stop at the hour. That's been a fascinating hour, a terrific presentation. I want to thank you both for presenting.
Sorry to interrupt, Jim. We're just going to give 10 extra minutes for Q&A.
Wonderful. Okay, that's great. That's even better. So in that case, we can press on. And I'm going to ask then another question about this. Iterate your way to success. Jeff and Zach, it's historically, when you had a cost plus arrangement like the Apollo program, where you could essentially build hardware and blow it up, and what it cost didn't matter much as long as you beat the Russians. You work in a different world now, where you're not beating the Soviets to the moon, but you do have competitors in the market who want to lift objects into low Earth orbit at the lowest possible cost. Does that change the way you approach this? I mean, when you think about designing new parts, are you thinking about how soon, how much initially? Or are you still designing, thinking about what's the best, highest performance design I can make?
I guess I'll take a crack at that first and say, there used to be an adage in the aerospace industry when I first started that said, pick cost performance, technical performance, or schedule performance. Pick two of the three, but you'll never have all three at the same time. And that was a battle that those programs from the 1950s till recently, they just couldn't really get around it because of the complexity that I talked about in the presentation. But I think with where we're getting our enhanced capabilities through advancements in Sapphire and other machines is we're getting to get all three at the same time. So I don't think it's the same today as it was in the 60s because they had different constraints, to be fair. And when at Interstellar specifically, when we talk about spacecraft systems and technologies from low Earth orbit and out that are reusable, that's obviously an extreme design case as well. But we're going to let the low Earth orbit, the launch to low Earth orbit folks continue to be successful and bring those prices down. They have a very effective system to do that. And I think they're always going to be focused on how do you bring the most cost-effective solution to the dollar per pound to orbit. We have a little bit different problem when we talk about in-space operations, but still, we're providing the lowest possible solution to meet that low Earth orbit to cislunar space to beyond need. So to answer the question, we're doing a lot of the same things, but we don't feel with the advancements that we're bringing in design, along with the machine advancements that are coming from machines like Sapphire, that we have to make those kind of sacrifices and we can still give a commercially priced product to the industry.
Yeah. Zach, a question for you from the floor, a very specific one. It says, as I recall earlier, Velo 3D still needed supports at 10 degrees or lower relative to horizontal. Is this a recent development?
Yeah, it's a great question. We were advertising, I think probably about 6 months ago, we had 10 degrees as kind of the limit of where we could get. But I think like all good manufacturing or engineering organizations, we've been trying to continue to push the limits. And through continuous improvement, we've managed to do so. So we're now able to print some pretty extended 0-degree overhangs, and we'll continue to try to improve those in terms of the surface finish and anything else we can do to broaden the application space for our system.
Yeah. Jeff, you showed an interesting image of injector plate on a Rocketdyne F1 engine. That specifically, in fact, was a pacing element in the entire Saturn V program and very nearly derailed the program. As you showed it there, that traditional injector plate, it really looks like it has machine tool thinking. It's essentially a two-dimensional structure, a little bit of surface structure. Now that you can think in 3 dimensions, does your engineering expertise or does your intuitive feel for injector design, does that change? Has it required going back to first principles, or can a good injector designer who thinks in CNC machining terms make that switch to additive?
Yeah, there's a lot to unpack there, but I'll pick kind of the low-hanging nuggets. The answer is, regards to how we think, that's precisely the point I was getting at in the presentation. You are correct in your assessment that F1 injector, one, it was complicated because it was so big. The bigger the engine is, the more likely you are to have stability problems. The more that you have a complicated fuel like kerosene, which is a long chain hydrocarbon that breaks apart in funky ways when it's combusting and doing things, lends itself to instability. So they had a lot working against them, which is why that development was so complicated. But they had very limited ways to produce that very large injector. And so, yes, we don't even think about injector designs that way anymore, at least within Interstellar and teams that I've built in the past. It's more like if you think about, you used to build it based on what you knew you could build, and you were limited in your thinking. And now, if you can think about what does the fluid want, what does the engine want to be 100% efficient, that is the shift in thinking that has enabled some very unique design approaches that are very unique to us that we're excited to see the results from and move forward with in our product line.
Jeff and Zach, with additive, at this point in the technology's development, there is not quite as broad an array of materials as might be possible with, for example, the ability to forge custom alloys as a blank and work from that. Working with materials you have at hand, do you have to do anything exotic, for example, film cooling or manipulating shock waves, or can you just go ahead and choose a material durable enough to handle those unbelievable temperatures you're talking about and still survive, the firing cycle?
If I take a crack at that one first, there is no substitute for experience, is my best way to answer that question initially. You do still have a limited selection of materials, whether it's additive or some other means that can survive these extreme environments. And so you really have to come back to your experience in design and how you utilize the whole system and your available propellant to keep the system at a temperature that's survivable and also reusable. So I don't find there to be any, there's a lot of things that go into picking the engine cycle. So I showed all those engine cycles, just kind of have an overview, but you have to be careful on how you construct the engine and the engine cycle to be able to take advantage of the materials that are available to you right now, utilize additive, and then rethink the whole design to meet your objective. But I personally, a few years ago, if you'd asked me that question, I'd have said, yeah, I feel really limited by the material selection. Today, I don't feel as limited because the materials we have available, we've really improved the properties significantly on. And so there's a really decent selection. Now, there's some other alloys that I would like to see matured that we will plan to use as we upgrade our products and systems. But I know that's coming on the horizon. So I'm excited about that as well, but I don't feel limited by it.
Yeah. Jeff, you mentioned turbo pump technology, specifically pre-burner gas generator cycles. It's historically, that's just about a mechanical engineer's worst nightmare. You've got unbelievable temperatures on one side, and you've got cryogenic liquids being pumped on the other, and these things are merely inches apart. I mean, that temperature gradient would drive anyone to drink. There's been talk about concentration gradients, composition gradients, a future where we're going to be able to make not just custom alloys, but a single part which has different composition from one side to the other. Is that going to come to your technology, to rocket engines?
Yeah, I think absolutely. I mean, eventually. I mean, I don't, at an R&D level, I see that happening pretty soon. On a flight level, I think that's still, probably 3 to 5 years from now. But Certainly some of these more exotics are going to find their way in. I think the real first hurdle to climb was just getting the industry to rethink. And when I say industry, the space industry to rethink and accept additive as a manufacturing method that can pass these rigorous certain qualification specifications. I think we're really getting beyond that at this point, which is going to allow us to fast track some of these new materials under the same type of certain qual programs we have today. So I'm excited about that. I think we're still a little bit further out on some of these custom material solutions, but I certainly think in things like turbo machinery, where you have these huge extremes, we'll definitely be leveraging that to our advantage.
Jeff, you've talked extensively about rocket engine design in this presentation. You've developed an additive technology that lets you make a wide variety of parts. Are you looking to a future where you design and build the entire system? Can we see the entire spacecraft coming out of Interstellar?
Yeah, absolutely. I mean, our vision, as I mentioned early on, is one of a spacecraft company that's really helping move people and cargo beyond low Earth orbit. And so I see that for us in our future. I think we're offering some unique things initially in the propulsion area, but then as we evolve our spacecraft technologies around our propulsion capability, you'll see Interstellar be using additive heavily with our propulsion technologies for these spacecraft applications. That's what's really exciting to us in our long-term vision.
Jeff, we have time for one more question here, and it's a really simple one. Why VELO3D? You've got multiple options.
Yeah, we have multiple options, and we work with a lot of different people and a lot of different machines, and we have great relationships with all of them. I think why VELO3D is because myself and my team have found some really unique attributes among the way Velo has approached printing that's different than anything that's out there right now. And so it's something that we wanted to explore. It's something we wanted to partner on and say, here's our extreme requirements, here's our innovative design philosophies. We want to unlock all these things with some new print capability. And Velo was willing to work with us to make these things a reality. And so I think the combination of the mindset Interstellar with the mindset at Velo was just kind of a match made in heaven in terms of being able to bring these things to the point where we are. I mean, the work you've seen us kind of tease a little bit today are things that happened just in the last few months. So we've known each other for a couple of years, but we've really accelerated that partnership to bring some exciting things to bear, and there'll definitely be more to come from us.
Jeff and Zach, well, we broke the 1 hour barrier, and I'm very glad we did. We got a lot of interesting insights into this. I want to thank you both for a fascinating presentation. I want to thank everyone who attended today for being with us on this. I'd also like to thank VELO3D for sponsoring today's webinar. So from all of us here at engineering.com, goodbye and thanks.